right, we're going to turn our attention out of solving some equations. We're going to focus on linear equations. We'll learn to solve different kinds of equations throughout the course, but right now we're solving these linear equations, which just means, what makes it linear is that the variable appears with just an exponent of positive 1. So we don't have 3 over x or 5 times the square root of x. We just have, 3x to the first, right? Like as we see in this example. And when we solve an equation, and when we solve any equation, we're just looking for the value of x that makes the equation true if we were to plug it in. So, real quick, we can show that x equals 3 is a solution to this equation, 3x minus 5 equals x plus 1, simply by substituting in the value. So, if I substitute in the value 3 for x, on the left side, we get 3 times 3, which is 9, minus 5, and that gives us 4. On the right side, 3 plus 1 is equal to 4. These are equal, so we can see that x equals 3 is a solution. Now, this is not how we want to solve equations, right? We don't solve equations just by plugging in values and seeing if it makes it true. But that is a way that we can verify, and this is how we check to see if our solution that we found is true. What we're going to do in this section is learn kind of an algorithmic approach to solving these types of equations, and there's one sort of general rule that we have to follow, and that is, if I perform an operation on one side of the equation, I also have to perform it on the other. I could think of an equation as a balance beam, and the equal sign is like the fulcrum. So I'm going to illustrate this technique, or illustrate this rule, right? This principle, and then what motivates our moves in the following 3 examples. These 3 examples are really simple, and you could probably even see what the answer is just by looking at them. The point is just to sort of illustrate and practice sort of what's going to motivate our moves. So we want to make moves that help us isolate the variable x. In this case, we're pretty much sticking with x, but the variable could be anything. But so in this case, what helps us isolate x? In part A, we are subtracting 3 from x. So if I want to get x by itself, I want to add 3. I am motivated to add 3, right? Because that's what will get x by itself. And because I want to add 3 to the left side, I have to add 3 to the right side. And here we get the unsurprising result that x is equal to 11. In the example in the middle, I am multiplying x by -6 on the left side. I want to get x by itself. So in order to undo that multiplication by -6, I'm going to divide by -6. I am motivated to divide by -6 because that's what will isolate the x. And because I want to do that, I have to also do it on the right side. And so we get the result x equals -5. And last, x is being divided by 2. I am motivated to multiply by 2 because that's what will isolate the x. And because I want to multiply by 2 on the left, I also have to multiply by 2 on the right. And we get the result x equals 20. Again, none of these results are surprising, but I'm just saying, I wanted to illustrate this principle, this general principle that we have to follow. We're going to be motivated to do certain operations on one side. We just have to make sure we keep the balance. So here's our basic procedure for solving linear equations. If there are any equations, we want to multiply both sides by the least common denominator to turn it into an equation without fractions. But next we just simplify both sides, so get rid of any parentheses, combine like terms. Then we're going to get all of our x's on one side and everything else on the other side. Then we'll be in a position, after we do this step here, we'll be in a position where we're looking at basically an equation probably like part B, maybe by part C, but most likely looking at an equation like we see in part B here. And then we're just one step away from getting the answer. So let's do an example. We've got some simplifying to do. On the left side, I'm going to distribute the 2. 2x minus 6, and then bringing down that minus 17. On the right side, going to distribute this negative 3. I'm going to be careful with my signs here. So I got 13 minus 3x minus 6. Now I'm going to combine like terms. On the left side, I've got negative 6 minus 17. That's a negative 23. On the right side, 13 minus 6 is a positive 7. So I got negative 3x plus 7. Now I want to get all of my x's on one side and everything else on the other. Now you can pick either side you want to get your x's on. I tend to default to the left. Sometimes I'll use the right side if it seems convenient. But I'm going to get all my x's on the left side, so I'm going to add 3x. Now I'm motivated to add 3x because I need to get my x's out of the right side. That means I need to also add 3x on the left side. And if I'm getting everything without an x on the other side, that means that I want to add 23 to this side. Right, that's what will get rid of the 23. That means I have to add 23 to this side. So notice, in this line right here, I am performing the same operation on both sides. The result is the equation 5x on the left, no constants. On the right, I've got no x's, but I've got equals 30 on the right. And now, to get the x by itself, x is being multiplied by 5, so I want to divide by 5, and I could do that as long as I also divide by 5 over here, and I get the result x equals 6. Now you could check your answer simply by plugging in x equals 6 to that equation, and you'll see that you get the same value on both sides. Let's do another one. Here we're going to solve for x. I've got some simplifying to do. I'm going to distribute the 4 here on this side, and I'm going to distribute the 3 on this side. That'll give us the equation 8x plus 4 minus 29 equals 6x minus 15. I've got some like terms to combine on just the left side. So I've got 8x minus 25 Now I've simplified both sides. I want to get all of my x's on one side, everything else on the other side. So I'm going to get all my x's on the left, which means I'm going to subtract 6x because I don't want them on the right side. And if I'm subtracting 6x over here, I need to also subtract 6x over here. And I'm going to add 25 so I can get all my constants on one side, and that means I also need to add 25 on this side. This leaves us with the equation 2x equals 10. And now to get x by itself, I want to divide by 2 on this side, and I can do that as long as I also divide by 2 on the other side. And I get x equals 5. Alright, let's solve one more equation here. This is an equation with fractions. So what I'm going to do first is turn it into an equation with no fractions, because we know how to solve those. And I'll just note that the least common denominator is equal to 20. My denominators that appear in the fraction are 5 and 4, so the smallest number that they both go into is 20. I'm going to multiply both sides by 20. Now that factor of 20 is going to distribute to each of these terms. So what I'm going to do is just rewrite this . So the 20 on the left side, when we distribute the 20, I'm going to have times 20 over 1 times 20 times 20. I'm writing it as a fraction next to the fraction just to make it a little bit easier. But the reason I'm multiplying by 20 is because it will cancel out these denominators. So in this first term on the left side, the 5 goes into 20 4 times. And then I have 4 times 2, which is 8, times 6y plus 1. And then 3 times 20 is 60 times y plus 1. On the other side, 4 goes into 20 5 times. So I have 3 minus y times 5. And then minus 60. Now this looks like an equation I already know how to solve. I'm going to distribute factors and combine like terms. So first we get 48y plus 8. And then minus 60y minus 60. Be careful with your signs. On the other side, I got 15 minus 5y minus 60. Alright, so combining some like terms, 48y minus 60y, that is a negative 12y. And then 8 minus 60 is a negative 52. On the other side, I've got a negative 5y, and 15 minus 60 is negative 45. Alright, let's get all our y's on one side and everything else on the other. I'm going to add 5y and add 5y. That'll get all my y's on the left. Then I'm going to add 52 because I don't want that 52 there, that negative 52 there, so I'm going to have to add 52 over on the other side. Negative 12y plus 5y is negative 7y. On the other side, the y's cancel. 52 minus 45 is 7. And now if we divide both sides by negative 7, we get y equals negative 1. Alright, so that's some practice solving linear equations. We're going to turn our attention for a little while to solving linear inequalities, because really we know already how to solve these linear inequalities now if we just add one extra or a couple of extra ideas. So first of all, we end up with an inequality if instead of an equal sign in an equation, we replace that with one of these signs. So we got less than, greater than, less than or equal to, greater than or equal to. And when I was first learning these symbols for less than and greater than in middle school, I would always get confused by them, which one meant which one. And then somebody pointed out to me that the less than sign looks like an L. So that's how I remember which means which. And before we solve these linear inequalities, first we're going to look at how we represent them or graph them, represent them visually. So picture a number line. An inequality will represent a range of values, a range of infinitely many values on the number line. So x less than 3, that's strictly less than. That means it could be any number less than 3 and as close to 3 as we want, but just not including the actual number 3. And if we write out a number line, so less than 3 means that it's all these numbers to the left of 3. But we cannot include 3, and I'm going to indicate that by drawing an open circle. Some people might use soft parentheses, curved parentheses there instead. It means the same thing. So there it is, graphed on the number line, and then it says, and write each inequality using interval notation. So interval notation here would be, let's see, there's no limit to how negative we can be, right? We can go all the way down. So that means our left endpoint is negative infinity up to 3. And we can't include 3, so that's soft parentheses. Infinity always gets a soft parentheses, like an open parentheses. Our next example, x greater than or equal to -1. So greater than or equal to -1, greater than means their value is on this side, but this time they're allowed to be equal to, so I'm going to use a solid dot. Other people might choose to write that as a hard bracket, and they mean the same thing. In interval notation, I'm going to use a hard bracket, square bracket, -1, comma, infinity. So that represents that range of values for x. And now last, maybe I have an interval that's bounded both above and below. And when you have a three-sided inequality like this, it is always written with less than signs. Because when you write it with less than signs, then that just, you can almost imagine yourself just picking this straight up off the paper and translating it directly to the numbers, the number line. So I'm going from -1 to 3. I can include 3, that's an or equal to. I can't include -1 because that's strictly less than. And if I were to write this as an interval notation, -1 open parentheses or soft parentheses because that's a strictly less than, and then hard bracket or square bracket on the right side because that's an or equal to. Alright, so solving linear inequalities. We already know mostly how to solve these inequalities because it's almost identical to solving an equation. There is simply one extra rule, and that is that if we multiply or divide both sides of an inequality by a negative number, then the inequality sign must be reversed. So let's solve some inequalities. Here the x's are already on the left side, so I'm going to get them by themselves simply by adding 7 to get that 7 out of there. So I get 4x greater than or equal to 12, and I'm going to divide both sides by 4. It's a positive 4, so I don't have to worry about reversing any signs. X greater than or equal to 3. So there is the answer written as an inequality, and then it says graph the solution set. So 3 is sort of the important number. It's an or equal to, so I'm going to write a solid dot. And then anything greater. I could write the answer in interval notation as well. Square bracket 3, comma, infinity. Infinity always gets a soft parentheses. Next, -3x less than 21. So there's only one step that we need to take to solve this, and that is divide by -3. That'll get x by itself. But I gotta be careful here. I'm dividing by a negative, so that means I have to flip that inequality sign. X is strictly greater than -7. Strictly greater than, so an open circle, and then greater than, so it's to the right. In interval notation, it would be a open interval, open on both ends, -7 to infinity. When you check an inequality, you got to remember that if you check the actual value, if you check 3 in the first one, if you check -7 in the first one, that's what will give you equality. So you want to actually pick a number somewhere in the shaded region also. You should get equality when you check it at the actual value you found, and then you should find that the inequality sign holds if you find a value somewhere in the shaded region. Alright, one more example here. We're going to get x's on the left. Now, when we were solving equations, I said you could really get x's on any side you want. It's really important to get x's on the left side if you're solving an inequality. If you solve an inequality, if your x's are on the left, then the inequality sign points in the direction that you're shading. And that's not true if your x's are on the right. It's also kind of cumbersome and considered clunky to write x's on the right side for an inequality. So let's solve this. We're going to subtract 8x from both sides. We're going to add 12 to both sides. And that leaves us with the inequality negative 2x greater than 14. And now we're going to divide both sides by negative 2. And when I do that, I'm going to have to remember to flip that inequality sign so x is less than negative 7. So it's a strictly less than, so that's an open circle. We're shading on the left. In interval notation, it would look like negative infinity to negative 7.